Okay, guys, so let's just talk a little bit about the sort of things we can do with this sort of test. When we were talking about paired samples, I was giving examples with people, but in fact, it's not just people that we can run paired difference experiments on. So, if a person is the subject, which we have multiple measures, for example, rating two different products. Here, Coke or Pepsi. Coke versus Pepsi. For IT, it's two measures. We've got quantitative and qualitative reasoning. We can have almost inanimate objects. Imagine that we have different mining locations, or if we're a, if we're kind of a retailer, we have different supermarkets, and we're doing two different techniques or two different promotions for the supermarket. We can actually pair based on the location. So this is a very general method. It's not just for specific people. And again, sales for different, say, supermarkets on different days of the week. Again, you'd have location and you would have measurement for two different days of the week. We can also have before and after. So the example we had before, we go on a diet, do we lose weight? We're at a supermarket, we change the way we do promotions, do we gain or lose sales? Okay, so just a little thought in general. Now, this is not an experimental design class, so we would kind of be do a little bit discussing this, but you'll mostly do it in Dr. Allen's and Dr. Lander's class. Let's just actually, before we do match design, let's just do and talk a little bit about different types of design. So the first is the repeated measures, and this is what we've been describing. We have, say, one individual and we have two different measurements. So we might have, a before and after. For example, we're measuring different people. Yeah, I'm trying to draw little stick figures here, but let's just draw a little stick and a head. And, how much weight we lose. So we have the weight in pounds. And this person didn't do any of the exercises they're supposed to do, and this person gained weight. So this is a before or after experiment. Um, one potential issue with this type of experiment is we have no real control group. In most in most of the experimental designs we've been doing so far, we'll have two different groups which we're comparing. Here we have, one different group. So it may be that, um, these people come to the weight loss center and, you know, something's going on in the weight loss center. For example, there might be, um, being fed really fatty food or something, or they've changed the exercise regime. There's no real kind of control condition here. We just have all these people before and after. And if something might, another example is the measurement of weight might be slightly off. So there's no real kind of control condition here between before and after. The other type of design is a counterbalance design. And this would be, for example, let's just think about Coke versus Pepsi. And we'd have people like, rating out of 10. So we have 8, 7, 6, 5, 7, 9, 5, 8, a bit of look back the chips. The key with counterbalancing is we'd have about 50% of people ordered A and B, in this case, Coke and Pepsi, and 50% B and A, which would be Pepsi and Coke. Now, there may be some what we call carryover effects. Like if I have one type of Coke, it may be really difficult to actually taste the second type of Coke because I'm still tasting the first type of Coke. So, we could actually we could actually have these carryover effects. One potential way of dealing with these carryover effects is, just have a break between the experiments. Have people drink a glass of water, do some exercises or something. Again, if people watch two different adverts, and it's maybe adverts to scare you out of stopping smoking and they're a bit traumatic, you're in a kind of intense emotional state after you've accounted for the order effect, but you're always going to have a different effect on the second advert because the first one might be distressing. So in this case, you would do something like we'd have some sort of a gap or exercise, and then B, and then B, and gap, and A. But we still can't completely eliminate some of these carryover effects. We can think about them in terms of experimental design. And this is what sometimes you'll call washing the effects. You're kind of washing out the effects, but there may be carryover effects. And in this case, we're going to use a matched pairs design. Now, what is a matched paired design? And let me go back. Let's keep my ink annotation still. Let's go back to my drawing board. Okay, here we go. So I'm gonna move around a little bit and get back to my pen. Okay, so imagine that we can't really, you know, we can't really run a kind of counterbalance design. So we've only got, for example, people go into, say, hospital, and they have a disease, and we can choose, for example, treatment 1 or treatment 2. These two treatments can't be taken together. It's maybe two different drugs or two different things, but if they're taken together, they will have a negative effect. So we can't run that kind of counterbalance design. What we can do is we can still run a paired design in that we will match up patients. So if we have a patient that, for example, is 35 years old, is in, low heart rate, good health, and then has certain symptoms. So maybe let's say there's 3 levels of symptoms, level 2. And then we have a second person who's very similar. We actually match these people up and consider them to be one person for the paired design. So in this case, we would have treatment 1 and treatment 2. And even though it seems like an independent samples, we don't have one person. Here in treatment 1, we will have this person, and treatment 2, we have this person, and we can still calculate the difference because we've actually paired people up based on shared characteristics. That's an example of a matched design. Now, these can be a little bit controversial. Again, when we talk about researcher degrees of freedom, you've got like an infinite number of matching schemes. If you have, say, 100 variables in your data, you could match on 2 or 3 specific variables that give you a significant result. They're designed to remove variance by having kind of similar people together. So you could almost argue with these, it's a way of picking a matching design until you get a significant effect. So again, massive researcher degrees of freedom here, so it can be potentially abused. So a match design, we will often, if we have available data, or we'll do some sort of pre-test to find a response, and if people are responding similar, we will pair them up. we can use naturally occurring pairs. For example, husbands and wives are considered to have the same um, living situation. If we have something about, how people fare in education based on development, we think that siblings would have similar levels of development. So we will actually pair up based on siblings and maybe give one person one treatment and the other sibling another treatment, or in this case, you know, educational training. And again, as I said, there's lots of degrees of freedom here in how you actually create the pairs. There is, because you're turning a two sample test into a one sample test, you do get that reduction in degrees of freedom, which means the t distribution is a little bit wider. But we usually, because we're removing variance, that kind of variance that we have within the groups, we're removing some of that. We do get a big increase in the t value usually. But I said it can be a little bit controversial. And one method, and it's way beyond kind of this class, but kind of quite one way of matching is called, there's a whole subfield called propensity score analysis. And this sort of analysis is used quite a lot by health researchers for obvious reasons. We can't give somebody two different treatments. And I've also seen it a lot, used in economics. And for example, by, quant researchers in IS and marketing. Okay, so we have an example here. We have a male and female salary comparison. We're pairing individuals. Now, it wouldn't be as simple as this. We're basically looking at graduate salary and thinking, okay, there's going to be a lot of variation. You're going to have people who would do like a high earning major, such as computing with a high GPA, and you've got people with a low earning major, like maybe sociology or art history with a low GPA. These people, if we did male versus female salary comparison, it would be difficult. We'd also have the fact that you'd have more males doing computer science than females. So it'd look like we're biased towards males, but in fact, it might just be we have more males in high earning subjects. So let's look at the data here. So we've actually paired males and females based on GPA. Now, this is a simple example. Usually you would pair on multiple variables, and you might do, for example, GPA and major. That would be a sensible comparison. And you can see here, I've done two different kind of tests. The first is I've done it as a paired difference test. So you see I've calculated the differences between each of the pairs. We got the alpha. So I calculate my, let's just stick x bar d. I calculate my mean differences. So I've got my mean differences here. I've calculated the number of differences. I've calculated the standard deviation of the differences. And I do exactly the same test that we did before. So if I've got an alpha of 0.05, we're going to do a two-tailed test. So 1 minus alpha over 2. As I said, it goes from Excel goes left to right. N minus 1, so 9 degrees of freedom. And this is my t calculation value, which is xd divided by s over root n. And you can see we get a significant result. We've only got a very small sample size. This wouldn't be significant at p equals 0.01. We could also do a confidence interval, and you can see the confidence interval doesn't go through 0, so it's equivalent to having a significant effect. Now we do the student's t-test that we did last time. So we calculate the mean of each group. We've got n1 is 10, n2 equals 10. We've got the standard deviation, the variance. We've got the pooled variance. Now notice here, because for example here we've got a 70,000 and 29,000, our variance in each group is very high, which is why this is less significant. We calculate the critical value. So you can see we have more degrees of freedom here. We've got 18 degrees of freedom as per our independent samples test. So in fact, our finishing line is a little bit easier. Not a lot easier. Our critical T is 2.1 rather than 2.26. But our actual calculated T, because this variance is so giant compared to the differences, is 0.07. So it's completely insignificant. Look at this p-value. Same with the confidence intervals. It clearly goes through zero. We clearly don't have much effect. So again, that's showing the advantages of this kind of paired score analysis. So we've got it in Excel. The same thing. I won't obviously go through the calculations in detail here, but let's just do it from the current slide. So as with the spreadsheet, we have the T alpha over 2. We're doing a two-tailed. We've got n-1 9 degrees of freedom. We've got kind of S, which was 434 root n. And we basically calculate the margin of error and then add it, or this would be the mean, basically the mean difference. And this is the margin of error. And we add and subtract, and we get everything's positive. It doesn't go through zero, so the equivalent of a significant result. Okay, and the hypothesis is there a difference between male and female salaries. So again, we define our mu d. In this case, it's going to be male minus female. We're going to do a two-tailed test, so equal to 0, not equal to 0. Test statistics as before, x bar d divided by sd over root n. We're going to use alpha over 0.05, alpha over 2 equals 0.025. We can look, we might as well do, we've not done one of these for a while. Whoops. So let's look at our statistical table. We have 9 degrees of freedom. And we have a two-tailed 0.05. So our t-value is 2.262. Let's go back here. So that's exactly the same as was in the Excel spreadsheet. Then we calculate the the calculated T, x bar d divided by SD over root n. And there's enough evidence that there's a significant difference between male and female salaries controlling for GPA. As I said, in a real life environment, we'd want to control for more particular variables than this. Okay, so let's kind of go to SPSS. And here we go. So keep my annotations for the moment. So we have this data. It's in paired samples ttest.sav. I loaded it in beforehand. So we have we only have 10 pairs here. So we're going to do a t-test, and it's going to be small samples. So our data really should be normal. As I've said before, I'm a little bit cynical about doing this sort of normality test because it's a small sample size. It's going to be very hard to prove non-normality. And if you have a large sample size, nothing is ever perfectly normal. So you'll always get some sort of significant deviation from the normal distribution. But it doesn't really matter for large samples because I said you can assume the central limit theorem kicks in. So let's just have a look. Let's go to test normality first. So let's go to Analyze, Descriptive Statistics, Explore. And we're going to basically look at our differences to see if our differences are normal. We're going to go to Plots. And we could have a histogram. I didn't put that in my slides. But we're going to do normality plot with test. And here we have descriptive. So the mean was 400, as we said before. And here we go, the differences. Both of our tests for normality, remember for these kind of tests, the null hypothesis is that the data are normal. The alternative hypothesis is not normal. Here our P is greater than any kind of standard significance value, so we can fail to reject non-normality. So for the moment, we can assume normal. As I said in this class, if you accept the null hypothesis, you really should know the power of the test, but I'm just kind of going through what's kind of general practice. This is a histogram of the differences. And again, it's pretty obvious we're positive here because nearly every difference is positive. And as I've said before, the closer to normality, this is the line of observed versus expected for the normal distribution. But these things are really hard to understand because then nothing is ever perfectly on the line or normal. We can have a little look at the difference just to see if there's any sort of pattern. Okay, so we can now do this test and just I've summarized the results for normality here. Reject H0 of data normality if P is less than alpha, and then kind of my warning. And one thing I put is even if we fail to reject, because we can never be sure it's normal, I would always calculate effect sizes, and also I'd run the equivalent non-parametric test to give additional evidence. If I said, small sample size, maybe some suspicion we're not entirely normal, yeah, why don't we run both tests to give us extra evidence? Okay, so very fiddly this test. Let's go back to SPSS. Go to Analyze, Compare Means, and Proportions. And we're going to do paired samples teeth test. Now, we're going to do the male in variable 1, and we're going to drag the female to variable 2. We can actually we estimate the effect size doing the standard deviation of the difference, which is basically our just standard, basically x bar d divided by s. Going to click. I don't think we need any options because our null hypothesis 0 can also do a confidence interval. And here we go. We get our mean, standard deviation, confidence intervals as we calculated, t-value as we calculated, degrees of freedom. And we also get the p-value, which we got in Excel, as a two-tailed test, 0.017. And we also get we even get some confidence intervals for effect sizes, which we didn't really cover in this class. But we get the estimates for the effect sizes, and we can see the effect size is quite high. Now, never do something once where you can do it in multiple ways. So let's just go to Analyze. Again, compare means and proportions. Now we're going to do a one sample t-test. And remember I said, the paired sample t-test is really just a single sample on the differences, but our null hypothesis is the differences is 0. So the equivalent of mu0 is 0. And click OK. We do it a completely different way, but we get exactly the same results. Same t, same degrees of freedom, same p-value. And the mean difference is 400. So two different ways of doing exactly the same test. And I got Excel to calculate effect sizes, but final slide. D is x bar d over SD, which is a large effect size. And there's sometimes you want something closer to an independent samples test. The only way you would reason to do that is if you're doing some sort of a meta-analysis, and the meta-analysis is you try and compare multiple studies by putting all the results on kind of the same consistent measurement basis. If we've got a mixture of independent samples tests and paired samples tests, we may want an effect size equivalent to the independent samples test. And here it's just x bar d we assume that the standard deviations are equal, so S1 plus S2 over 2. So this is just the equivalent of the, remember we did the Cohen's D and the Glass's G. This is almost just the equivalent for even sample sizes. And we see with much, much lower effect size because it takes away much of this effect, kind of what we sometimes call a correlational effect for the paired samples. We get a much kind of weaker effect there size. We don't even get a small effect size for that. Okay, so that's paired t-tests. And we're just beginning to talk about correlations when we have these kind of paired samples, which would lead us nicely on to the correlation check.